As the field of nanotechnology has advanced, metallic thin films have become necessary for emerging new technologies such as third-generation photovoltaic cells, photodiodes, and many other semiconductor devices. Dr. Turak's lab works with these new emerging technologies and needs a method to not only build these thin films, but to build multi-layered thin films in order to improve the efficiency of these devices, as well as to build other devices such as Bragg lasers, waveguides, and more.
Current deposition processes used in her lab, such as spin coating and dip coating, are able to create monolayer thin films. However, they are not able to create multi-layered thin films, as the solvent used in the coats will damage the previous layer. This means new techniques must be used to create multi-layered thin films.
One new technique for creating multi-layered thin films is electrospray deposition, or electrohydrodynamic deposition. In electrospray deposition, a solution is slowly sprayed through a capillary nozzle in a high voltage field onto a substrate. This system deposits only the nanoparticles, with all of the solution evaporating, meaning that the multi-layered thin films can be created. Dr. Turak's lab currently has a handmade solution using duct tape to align the capillary nozzle and viewing camera to a plastic bucket. This results in a system which takes 1 to 2 hours to set up with variable results in the final deposition.
Our solution is MEDoNa, modular electrospray deposition of nanoparticles. This is a modular electrospray deposition device which is able to create monolayers of metallic nanoparticles in a safe, effective manner.
It uses an enclosed input system to connect both the solution and high voltage to the capillary nozzle, a precise motor-controlled stage to position the substrate and bottom electrode, and a control system which will monitor the deposition process via computer vision and provide feedback to the user to ensure an evenly distributed thin film is formed on the substrate.
We have designed, printed, and constructed a full enclosure for the Electrospray system. This system consists of a majority of 3D printed parts to minimize cost and maximize modularity. It also includes a clear acrylic window for the user to look through and watch depositions live. This system is entirely modular except for the laboratory equipment, the motor, and the stage. The system can be constructed in under 5 minutes. The Electrospray system is then set up vertically with the nozzle above the substrate, which rests on the bottom electrode. The bottom electrode is a 10 centimeter circular aluminum foil electrode, which is the optimal size to ensure that there is an even spread of nanoparticles across the entire surface of the 2 by 2 centimeter substrate.
The system is then controlled to have the optimal voltage and distance between the nozzle and the bottom electrode. This deposition system has been modeled to ensure that all solution is evaporated by the time the nanoparticles hit the surface. In order to have all the solution evaporated, the distance and voltage must fall within a modeled range, and a Taylor cone must be formed to ensure all droplets are charged. Taylor cone formation is ensured through a computer vision system which uses edge detection to calculate the semi-vertical angle of the cone to ensure that throughout the deposition process the Taylor cone is maintained. The distance between the substrate and the electrode is then controlled by a motor connected to a scissor lift through a gear system. This can control the height of the stage up to 1 millimeter accuracy.
The first tests were performed using a static stage at a pre-calculated distance to verify that the electrode, Taylor cone imaging, and droplet modeling results were all accurate. All systems functioned as expected, but due to problems with the solution tubing, a stable Taylor cone could not be formed, and the deposition was unsuccessful. The next tests were performed with the full system to increase the stability of the Taylor cone. Subsequent tests performed had a much more stable Taylor cone, although there were a few drops which meant that the deposition was not fully uniform across the substrate.
For the full test, 3 ellipsometry measurements were taken in 3 different observed regions of the substrate. The thickness of the deposition in a thin region was 3.12 plus or minus 0.005 nanometers. The thickness of the deposition in the ideal region was 17.59 plus or minus 0.387 nanometers. And the thickness of the deposition in the middle of the substrate where the drops fell was 62.42 plus or minus 0.596 nanometers.
For the future, the elimination of the drops falling onto the substrate is the highest priority. To do this, we are going to investigate using a horizontal setup rather than a vertical setup, which will require further modeling of the droplets to ensure that gravity does not cause the deposition to become uneven. We will also investigate the use of a tertiary electrode and higher resolution camera to further improve the stability of the Taylor cone. The case and motor control system will be further improved to stabilize the electrospraying system and to accommodate any other changes required.